Hello, welcome to Cornerstones of Math, and today I am going to prove what was teased in my last video, the generalized identities. So when theta equals 2 pi divided by n, where n is a natural number, prove that cosine theta plus cosine 2 theta plus cosine 3 theta plus all the way up to cosine n theta equals 0, and sine theta plus sine 2 theta plus sine 3 theta plus so on plus sine n theta equals 0. And I will prove this with two beautiful methods. The first method is the geometric proof, similar to my last video. But wait, didn't my last video use the symmetry that only works for even numbers? Well, that's why in this video, I will use vectors. Consider a unit circle. Since this theta is 2 pi, which is the entire circumference, divided by n, if we take points P1, P2, P3, and so on the circumference by rotating theta counterclockwise every time, we have total n points that divide the circle into n arcs with equal length. Moreover, the coordinates of these points are cosine theta, sine theta for P1, cosine 2 theta, sine 2 theta for P2, and so on, all the way up to cosine n theta, sine n theta for Pn, which is chosen to be the point 1, 0. We can think of these points as position vectors, where vector OPK has components of cosine k theta and sine k theta. Now this is an example of the case where n equals 5. Yes, I wanted to show you the case when n is odd. In the figure, you can see these 5 position vectors, vectors OP1, OP2, OP3, OP4, and OP5. Now let's rearrange these vectors in this way. So this is vector OP1. Next, we draw vector OP2 in a manner that the tail of vector OP2 coincides with the head of vector OP1. Then, this angle must be theta because vector OP2 is just vector OP1 rotated by angle theta counterclockwise. Next, we draw vector OP3 so that the tail of vector OP3 is on the head of vector OP2, then this angle is theta, and so on. Then you can see that for our example of n equals 5, the 5 vectors form a regular pentagon. And you can guess what happens when there are n vectors instead of 5. In the case of n vectors, vectors OP1, OP2, so on, and OPn form a regular n-gon. Now what's important with this n-gon is that it is a closed shape. And we know that if some connected vectors form a closed shape, their sum is a zero vector. And since these vectors have these components, from x components we obtain cosine theta plus cosine 2 theta plus so on plus cosine n theta equals 0. And from y components we obtain sine theta plus sine 2 theta plus so on plus sine n theta equals 0. And the proof is complete. So that was the first method, the geometric method. In the second method, I will not explicitly use geometry, but rather use other trigonometric identities to solve the problem. More specifically, we first want to prove these identities. So the first one is cosine theta plus cosine 2 theta plus so on plus cosine n theta equals cosine n plus 1 theta over 2 times sine n theta over 2 over sine theta over 2. And the second one is sine theta plus sine 2 theta plus so on plus sine n theta equals sine n plus 1 theta over 2 sine n theta over 2 over sine theta over 2. Now the coolest thing about these identities are, they are true for all valid values of theta. That is, not just our special case of theta equals 2 pi over n. Here, valid means not making the denominator 0. So we are basically proving something that holds for more general case, which is pretty cool. Now how do we prove this? Some of you might think of using angle addition formulas, which are essentially derived by geometry. Well, we are not directly using angle addition formulas, but we use these formulas, which are directly derived from angle addition formulas. These formulas are called product to sum formulas because they allow us to convert the product of trigonometric functions into sums and differences of trigonometric functions. Moreover, if we let alpha plus beta as a and alpha minus beta as b, which gives alpha as a plus b over 2 and beta as a minus b over 2, and rearrange a bit, we obtain these formulas, which are called sum to product formulas. As the name suggests, these formulas allow you to convert the sums or differences of trigonometric functions into products of trigonometric functions. So to recap, we are going to use these product to sum formulas and these sum to product formulas. Now for the first identity, we have this sine theta over 2 in the denominator of the result. Therefore, instead of adding up cosine k theta, we try to add up cosine k theta times sine theta over 2. Here we have a product of cosine and sine, so we apply this product to sum formula. Then we have 1/2 times sine sum of these two angles, so k theta plus theta over 2 minus sine, now the difference between these two angles, so k theta minus theta over 2. And let us write this as 1/2 sine k plus 1/2 theta minus sine k minus 1/2 theta. So we have this summation of 1/2 sine k plus 1/2 theta minus sine k minus 1/2 theta. If we take the sum from k equals 1 to k equals n, when k equals 1, we have 1/2 times sine 3 over 2 theta minus sine 1 over 2 theta. And when k equals 2, we have 1/2 sine 5 over 2 theta minus sine 3 over 2 theta. And you can see where this is going. For the final term where k equals n, we have 1/2 sine n plus 1/2 theta minus sine n minus 1/2 theta. This is a telescoping sum where most of the terms cancel out. So this and this cancel out, and this will cancel out, and in the end this term cancel out. So we have this minus this, so we have 1/2 sine n plus 1/2 theta minus sine 1/2 theta. And here we have sine minus sine, so let us apply this sum to product formula. Then we have 1/2 times, we have 2, and cosine sum of these two angles, so n theta plus 1/2 theta plus 1/2 theta, so n plus 1 theta divided by 2, and sine, now difference between these two angles, so n theta plus 1/2 theta minus 1/2 theta, so now it is n theta over 2. And if we cancel out these two, we only have this part, which is the result of this sum. So we have proved that this sum, which is this sum, is this. And we are dealing with the cases where this sine theta over 2 is non-zero. So if we divide with sine theta over 2, we finally obtain sum of cosine k theta, which is cosine n plus 1 theta over 2 sine n theta over 2 over sine theta over 2, which is the first identity we wanted to prove. And the second identity can be proved in a similar way. So instead of this, we calculate this, and we have product of sines, so we apply this product to sum formula. Then we have minus 1/2 cosine sum of these two, k theta plus theta over 2 minus cosine difference of these two, k theta minus theta over 2, and let's write this as minus 1/2 cosine k plus 1/2 theta minus cosine k minus 1/2 theta. So we have this summation instead, minus 1/2 here, cosine k plus 1/2 theta here, cosine k minus 1/2 theta here, which is also the telescoping sum. So cancelling out, we have these terms. So we have minus 1/2 cosine n plus 1/2 theta minus cosine 1/2 theta. And now we have the difference between cosines, so we apply this sum to product formula, which gives So minus 1/2 is now multiplied by minus 2. And we have sine n theta plus 1/2 theta plus 1/2 theta. So n plus 1 theta over 2 times sine. Now this minus this, so n theta over 2. So these two cancel out. So we have this as a result of this summation. So we have the summation of these terms. So if we divide by sine theta over 2, we obtain this. The summation of sine k theta equals sine n plus 1 theta over 2 sine n theta over 2 over sine theta over 2, which is the second identity we wanted to prove. So we have obtained these general identities, which hold for all values of theta that do not make the denominator 0. For our special cases where theta equals 2 pi over n, notice that sine n theta over 2 right here in the numerator becomes sine n times 2 pi over n over 2, which is sine pi, which is 0. So the right hand sides become 0. Therefore, these identities reduce to cosine theta plus cosine 2 theta plus so on plus cosine n theta equals 0. And sine theta plus sine 2 theta plus so on plus sine n theta equals 0. And that's all for today's video. Thank you all for watching, and please hit that like and subscribe buttons to enjoy more fun math problems, and I will see you in another video.